Okay, so I've sort of made like a little outline picture thing. If you want to take a look at this or pause the video and look at it a little bit more, this might help you to picture what's going on at different functions. All right, but besides that, I'm going to move on here. Example 5. This is a great example to kind of combine a lot of the ideas here. So we have two continuous functions. So let's see, we're going to look, where's f increasing? This is a graph of the derivative. So it's going to be increasing where our derivative, anywhere that our derivative is positive. All right, so these values. Where's our derivative decreasing? It's going to be wherever the derivative is negative. So these values. All right, that's where our function's decreasing. This is a similar idea. Okay, this is asking exactly the same thing. There will be local extrema. Okay, there's going to be a minimum, relative minimum, at x equals 0, and that's because the sign of the derivative changes from negative to positive. There's also going to be a relative minimum at x equals 8 for the same reason. The derivative goes from negative to positive. So there'll be a relative maximum at x equals 6, okay, because it's going from positive to negative. Where is f concave up or concave down? All right, so remember that's the second derivative. So we're looking for where the slope is positive versus where the slope is negative. All right, so here, 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 and here, the slope or the second derivative is 0. All right, so we're going to have concave up wherever that, wherever that second derivative, wherever the function, the actual derivative is increasing. So from 0 to 2, and also from 3 to 5, and from 7 to 9. All right, so that means that our f function is concave down from 2 to 3, because the derivative here is decreasing the slope, and also from 5 to 7. And that gives us inflection points, all right, at x equals 2, because the sign of the second derivative is changing from positive to negative. All right, x equals 3, because it's going from negative to positive. X equals 5, because it's going from positive to negative. Okay, and also x equals 7, because it's going from negative slope to positive slope. Assuming that f of 0 equals 0, we're going to sketch a graph of f. All right, so we got 1 point. What this is telling us here is that our graph is decreasing, right? And it's also concave up. So it's decreasing until we hit this part. So it's decreasing, all right, and it starts out at a steeper rate and then it kind of evens off. And here the derivative is 0. Now it's increasing, right? It's increasing from 1 all the way to 6, but at varying rates. So we're starting out concave up. All right, and then this changes to concave from 2 to 3. It goes concave down, and that's because it's decreasing a little bit. All right, so it's concave down. Maybe it could look something like this. I don't know. And then it goes back to concave up. All the while, it's still increasing. All right, concave up, concave up. Keep going. Oh, I should have made that straight, but that's okay. Concave up. And then here, all right, let's see, you're concave down from 5 to 7. So I need to just tweak that a little. And then here it starts to decrease all the way until this point, and then it gets really steep. There you go. That's a possible graph of f of x in purple there. So can we see where it attains its maximum or minimum. And keep in mind, we were talking about absolute or global at that point. Well, it appears that this is going to be the absolute minimum value, okay, at x equals 1. We said we had a relative min. Oh, I said 0 earlier. I think that should have been a 1. All right, there we go. Absolute minimum value at 1. Because for this time, it's decreasing. And then all the way from 1 to 6, it's increasing. So it's probably not going to get much lower. All right. But here, it's kind of hard to tell. Is this our absolute max? Is this our absolute max? So without getting more specific or getting a few more points, we're not going to be able to tell that. All right. I would like you to try this graph right here, the second one. Just try it. We're going to talk about it in class. All right, because I think it's really important to pull it together, and I want to hear your contributions. All right, so this is our last example. I'll do one of these. I'll do the hardest one, which I think is the first one. Okay, and then I want you guys to try this, and again, we can go over it in class. You're going to have plenty of time today. So this function, the domain, is actually all real numbers, even though they have fractional exponents. So I'm going to write a little bit smaller here. All right, so we'll start off by looking at our first derivative. So we get what, 10 thirds x to the 2 thirds minus 20 thirds x to the 1 third. So we're trying to sketch a graph of this. So we want to look at maybe some different things, symmetry, end behavior. These are things that you should look at on your other two. Maxes, mins, all right? Increasing, decreasing, constant, concave, concavity, concave up, concave down, points, possible inflection values, critical values. There's a lot of different things to look at here. All right, so by looking at this function, I might be able to find some critical values. All right, I think it'd be easiest to factor out least powers here. So x to the 1 third, right? That would give us that. And then minus, and looks like just 2. All right, so what are our possible critical values? Where would this equal 0, or where is this undefined? So it's not going to equal 0. I mean, it's not going to be undefined, but it will equal 0 at 0. And also, if you solve this, okay, move the 2 over, then cube it, you're going to see that there's another possible critical value at 8. So these will have to come back to. All right, we can use the first derivative test if you want, but it's not too hard to check the second derivative. All right, so then I'm going to go back to this form and check the second derivative. So we have 29ths x to the negative 1 third, and then minus 29ths x to the negative 2 thirds this time. All right, factor out least powers. We get 29ths x to the negative 2 thirds. And let's see if we negative 2 thirds plus what gives us negative 1 third. All right, so we get x to the first and then minus 1. So that looks a lot easier now. So we have 20x minus 1 all over 9, and I'll just rewrite that as x squared, cube root of that. All right, so now we can determine f double prime is going to equal, it'll equal 0 when x equals 1, and f double prime of x doesn't exist when x equals 0. So these are our possible inflection values. All right, so let's start to pull this together. If we check our critical values, f double prime of 8, if you plug in 8, you're going to get positive values. So that tells us, because it's that, we have a relative minimum. at x equals 8. All right, if we check 0, oh, well, we can't, it's undefined, so we're going to have to use the first derivative test for 0. All right, so plug in 0, we have x. Look at our first derivative. Okay, plug in numbers like 1 and -1. If we plug in 1 to our first derivative, this part will be negative, this will be positive, so we'll get a negative value. Plug in -1, all right, this will be negative, this will be negative, this ends up being positive. So it looks like we have a relative maximum at x equals 0. All right, so we have some different values. And let's see, we know we have a relative minimum at 8. So let's just figure out what that point is. All right, f of 8. So it's 2 times the cube root of 8, which is 2 to the 5th. 2 times 32, so it'll be 64. And then we have minus, so it'll be 2 to the 4th times 5. I think that's minus 80. So I believe it's negative 16. All right, so we have a point 0, 0. That's just an easy one, okay? If you plug in 0, you get 0. And we have a point 8, negative 16. Okay, we didn't analyze all of our points, but we know that this is a relative minimum. So I guess we should determine concavity here. Let's see. So where am I talking about? Let's talk about maybe 0. It doesn't really matter what values we pick, but it's concave. Oops, let's make that 1. I'll plug in, say, -1 to our second derivative. Up top, we're going to get a negative. On the bottom, we'll get a positive, so that's negative. On the right-hand side of 0, maybe like 1/2. If you plug that in, you get a negative on the top, positive on the bottom. So it's concave down in that area. All right, and then what if we plug in, say, 2? That's positive over positive, so we're going to have concave up. All right, so we're going from concave down, and we have a relative maximum, and then concave up, and we have a relative minimum. So it should look something like this. Check on your calculator to make sure, and remember that this is negative 16 and that's 8, so you're going to have to extend your regular window. And hopefully it looks something like this. Alright, I'd like you to try to sketch a graph of these using whatever math you need. For this one, if you know a lot of things from pre-calc, like the symmetry, the end behavior, you increasing, decreasing, maybe, discontinuities, you might be able to draw that without doing any of this work. All right, same thing over here. Look at the end behavior. Check out the symmetry. That'll give us horizontal asymptotes and makes it really easy to graph. All right.